Hey everybody, in this video we are working on a unit of inequalities, and I hope to be the person who shows you an efficient, valuable, accurate, an all-around wonderful way of solving your inequalities, of how to think of them. And I hope that it stays with you, because this technique will be a huge time saver, accuracy saver in calculus, if you go to calculus, and just in general to help your overall understanding. So section 1 is linear inequalities, back to basics. Section 2, absolute value inequalities, and section 3, where we are right now, are polynomial inequalities. Section 4 will be rational inequalities. But once you understand the concept through the polynomial and rational, you can really just go about doing more or less any type of inequality in this fashion. So let's get into it. So here it says, solving a polynomial inequality, example 1. We're going to solve and graph the solution set on a real number line. I'm also going to have us write the final answer in interval notation, which is just in general a good habit for all of us to have. All right. So first of all, you want to recognize what kind of equation are you looking at. And yes, indeed, it is a polynomial. We have 2x² plus x is greater than 15. Now, more specifically, this polynomial is actually a quadratic. And in a previous unit, we went over how to graph polynomials. And if you can just recall that information, if you didn't just cram and learn it for a day, if you actually put it into your long-term memory, you should be able to recall some of the key information. So I'm going to highlight some of that for you, but in the upcoming examples on this unit, I will be moving faster and faster through everything. Now, for one thing, we want to find the end behavior, we want to find the x-intercepts, we want to find the local behavior. And that's how we're going to decide whether or not this particular polynomial, this quadratic, is, when we have it all set up, either positive or negative. In other words, greater than 0 or less than 0. So like solving any polynomial equation, solving a polynomial inequality does also require us to get it to have 0 on one side of the equal sign, or inequality sign in this case. So that's where we're going to start first. So the first thing I'm going to do is subtract 15 from both sides. I really don't think I should have to show you this step, so I'm going to get rid of it. But yes, that is how we're starting. I'm going to make sure, in the event that I have like terms, obviously I combine them, and that I keep my terms in descending exponential order so that it is set up best for me to visually realize how to continue the problem. So now that this is in standard form, like I mentioned before, I want to get my x-intercepts. We get our x-intercepts from using something we refer to as the zero product property. Basically, we get it equal to 0, we factor, we set each of the factors equal to 0, because essentially we're saying oh, if y equals this thing, that's your output, your y value gets you on your x-axis. If y equals 0, what x values correlate to that? And boom, those are your x-intercepts, right? So again, it has to be 0. It's called the zero product property. It's not the 15 product property. It doesn't work for another number, okay? Just don't try to argue it. Just trust me, okay? So I'm going to go ahead and factor. If you don't know how to factor really well, if you are very slow at factoring, please go to my factoring playlist and go watch AC Method, and please do yourself a favor and learn how to factor. So here I'm going to make my outer 6x, and I will make my inner 5x. And if I make it negative 5x and positive 6x, my middle term is positive 1x, which is good. Last, negative 15, and first times first is 2x². Now, I know I'm writing greater than 0, but when I'm getting my x-intercepts, okay, even though I have greater than 0 still written over here, for the step of getting my x-intercepts, for just a moment, right, I'm basically going to consider it as equals, because there is no real correlation to the inequality with my x-intercepts at that point, okay? So I'm just getting my x-intercepts, all right? No inequality symbol, please, and triple please. Okay, so there I am. Those are my two x-intercepts. Now, what I'm going to do is I'm going to consider the graph. Now, I would argue that more than 90% of teachers, textbooks, curriculums will have this taught to you using testing of intervals, which I find to be time consuming, and I feel like it disconnects you from the bigger picture, literally and figuratively. And I think this way is going to be quicker, more likely to avoid careless errors, and will keep you connected to how to graph. So this is positive 2x². When you have a positive leading term, that means that your graph is finishing pointing upward on the right side. All right, if you want to go back and watch my graphing polynomials video, by all means, go ahead and do that. When it is not just positive, but when it's also even, okay, so even powered right there, the squared, that means that my left end is going to be behaving the same way as my right end. Both even, both same, so both up. Okay, now my x-intercepts are, as I found, 5/2, which is 2.5, and -3. Obviously, -3 would be on the left, and 5/2 or 2.5 is on the right because, you know, numbers and how they work. Now, when I taught graphing polynomials as well as graphing rationals, which if you need to be the best grapher ever, go watch those videos, please. I told us that we're not just going to do end behavior, right? So what we just did over here with the yellow and blue highlighter, end behavior, positive leading term, right side is up. Even exponent or even degree of your polynomial means the beginning is the same as the ending. So the left side will be the same as the right, up and up. That's our end behavior. End behavior is asking us how the graph behaves on its ends, like the ends of a shoelace. So the fact that it's up on the far left over here and up on the far right is our end behavior, as x, essentially, or your input, is going out toward either positive infinity to the right, where's your y going? Or as x goes to negative infinity, the left of the number line, where's your y going? But not only do we want end behavior, we also want what I call the local behavior. And local behavior, which I will call LB. Local behavior is determined by the degree, or not degree, sorry, better word. Degree is the power of the leading term of your polynomial in standard form. I want to consider what we call multiplicity. Multiplicity is the degree of the factor that your x-intercept came from. Both of these factors have a degree of 1. So that means my local behavior is, I'm going to write L, and that is for linear. If those factors were to the second power, my local behavior at my x-intercept would be quadratic. As you zoomed in on that spot, it would basically touch and bounce off the x-axis right there. And then if it was third power, it would be cubic, and basically it more or less ping-pongs back and forth to being sort of quadratic and sort of cubic from here on out, right? So my local behavior is linear at both of these, so I'm also going to label a little L by both. Good habit to have, because eventually you'll have tons of x-intercepts and vertical asymptotes, and this will be a big old mess, right? So I'm going to go ahead and draw this now. So if I know my graph is finishing pointing upward, right? I also know this right here, -15, is my y-intercept. Like, I know I have a point down here. If that helps you, by all means, you could use that. I mean, I don't think we need it, but it is what it is. So here, x-intercepts, linear local behavior means I'm going to cut through like a line. So if you were to zoom in right there and you only looked at the graph really close, more zoomed in than I even am, if we were really, really zoomed in, well, that would look like, imply, or suggest, maybe mislead us to thinking, oh, well, this is a linear equation. But if you zoom out, you'll realize, oh, it's not. It just locally looks like a linear, right? So now it's a polynomial. Those are smooth and continuous, no sharp edges. So I know I have to turn around and get to my other x-intercept. It's also linear in behavior, cut straight through, and there we go. Now, you might be saying, this didn't say to graph. What are you doing, you crazy person? Well, this normally, without someone talking every step of the way, should take you a matter of seconds, okay? Now, what I'm doing from here is I'm considering this, greater than 0. Well, where the heck is 0, you may ask? 0, when y is 0, it is your x-axis. Y is 0 is not the y-axis. Listen to me again. y equals 0, output being 0, is not the y-axis, that is the x-axis. That's saying your height, your value is at 0 at that moment. And I want to know, when is this greater than 0? In other words, when is it bigger than 0? Greater than 0 is another mathy way of saying positive. Or we could say it's above the x-axis. So this is greater than 0 when it's above the x-axis. And if I consider that, it's basically going to be looking over here. So specifically, I'm really considering this little piece here, it's above, and this little piece here. And all I have to do is describe that interval. So now imagine that this red graph over here, oh, that crayon is so big. Consider this little graph right here melts down into the x-axis. What part is being covered, you know? This red part over here melting down into this axis, what's being covered? So my interval notation, my final answer to this question, okay? Please humor me. This is just explaining how we do this. When I get to the other examples, you know, I'm going to kind of fly. This is your tutorial, right? But it's from negative infinity, comma. Let's give myself a little bit more space than this. It's a little cluttered if you ask me. So final answer, negative infinity, comma, -3. And it says greater than, not equal to. So I'm just going to use a parenthesis. Then union, because I'm uniting it. I'm saying and, another section. And 5, or really or, 5 over 2. Again, it doesn't have a bracket because it's not including it. It's just greater than 0, not equal, comma, infinity, to the right forever, parenthesis. Infinity's always got a parenthesis because you can never actually reach infinity. We just approach it forever. So there is my final answer to the question in interval notation. If you truly needed to draw this on a number line, it's essentially the number line that I have up there, right? -3 and 5 over 2, right? 5 halves, same numbers. And we shade here, open circle. It's not a hole. So I was getting that today from some students, like, oh, so it's a hole. No, it's not a hole. It's an open circle, just signifying that that point is not included. It's similar in concept to what you think of when you think of a hole. But that's the end of this. Other teachers are going to say to you, find your, critical numbers, put them on your number line or so, and then test the intervals. Basically pick a number in each interval, test it into your inequality, figure out if your output is positive or negative, mark up the intervals, and then choose the appropriate intervals. I just think that if you're going to mess up doing that method, you're not going to catch your mess up. You're just going to carry on. But if you consider it graphically, eventually you won't even have to draw the picture fully. You will probably make it look like you're testing intervals, and you'll get the final correct answer at the end of the day. That's the end of this video. In example 2, we will be looking at a cubic, so check for that one. And after we finish this unit, section 3, whatever you want to call it, we'll be doing rational, where we have to figure out where the function equals 0 and where it's undefined. And those are a ton of fun. So if you are doing something in calculus known as your, say, first derivative test, you are probably looking at figuring out when your derivative is positive or negative. Hopefully this lesson helps you. And that's the end of this. So if you love it, what was it? I said something that kind of rhymed yesterday. And, if you can appreciate, thumbs it up. So thumbs up if you appreciate, but now where's the thumbs up? It's buried. Oh no, my thumbs up is lost. I can't do it. But thumbs up if you appreciate, thumbs down if you hate. Questions, comments, concerns, requests, feedback in the comments section down below. Check the upcoming playlist on the screen and the other videos that I'm also going to list and organize for you in the description box. Sorry, I'm blabbing. Longest video ever. Sorry. Bye for now. Adios.